All right, so welcome to this class here in AP Calculus A-B. We're talking about linear approximations today. Linear approximations. We're going to start off by studying this graph. The graph in red is the graph of y equals the square root of x. Okay? And you see here at the bottom of the screen we have 0, 0. Of course, the square root of 0 is 0, right? We also notice that the square root of 4 is exactly 2. Okay, so I have this point on the red graph highlighted. And what does this blue line represent? Go ahead and shout it out. What is this blue line?
Linear.
It's linear, yes. It's a line, so it's linear, yeah. It is I heard it over here, it's a tangent, okay? So where does it appear that this is a tangent to? The point, what?
4, 2.
Yeah, 4, 2. Not 2, 4, but 4, 2, okay? So yes, this blue line is a tangent line, and the point of tangency is on this red graph at the point 4, 2. X equals 4, y equals 2, okay? Everyone good there? Now, the whole idea of linear approximations. Now, what calculus can do is to help us approximate things quite precisely. So if we're talking about a guess or an approximation, in calculus we can use calculus methods to have a very, very good approximation. And we're going to do some examples here. We're going to focus on this one here today. But we can see that using the tangent line to a point, we can calculate values immediately surrounding that point on the graph fairly accurately. So this is what I mean. I'm going to zoom in here. And as you can tell, when we zoom in, okay, even by the thickness of these lines, when you get close to the point of tangency over here, okay, it appears what? It appears that the tangent line is almost identical to the graph itself, right? So that is very interesting. Now, the further you get away from the point of tangency, the more that the straight line, the tangent line, and the graph itself start to diverge, right? So as you get further and further away from the point of tangency, we see that this blue line and the red line start to separate. But if we take a look at this area right here, it can almost be said that the tangent line and the graph in this small area, they're almost identical, right? So let's say that we weren't able to calculate the points on the red line, but we were able to determine what the slope of the tangent line is, let's say, and we knew that what the values of this point were, okay? So we know the function, we know this point, we're going to use a tangent line to approximate what the values of the red graph are using the tangent line, okay? So we're going to use the tangent line to approximate values on the graph itself because, as we can see here, they're virtually identical. So what's an example of this? Well, let's say this is the point, we said this was the point 4, 2, right? And I'll zoom back out a little bit here. So this is the point 4, 2 for y equals the square root of x, okay? Well, that's great. I know that. And I know what the value of this graph would be at 9, right? It's going to be 3. And here's 3 up here. So there's the point right there. But I don't know offhand, without actually getting a calculator and finding out what the values of this red line are, I wouldn't be able to guess very closely what the value at 7 would be. I wouldn't be able to guess 6 or 5 either. I know 4, I know 9, right? Because those are perfect squares. So I would be able to say, hey, if I wanted to know what 4.2 or 4.3 would be, I could use the tangent line to guess a point. So what I'm going to do is I'm going to, actually maybe I'll just use this graph here, okay? I'll use this graph. Now you've sketched this out, and so watch what we're going to do here. I'm going to just erase some of this stuff, okay? So this is the point right here. This is f of x, right? Now, if the a value, if the x value was 4, let's say a is 4, this is f of a. Does that sound right? A is 4, this is f of a. And I've zoomed in so my pen is really thick right now. But this is f of a. Okay. F of x and the point on the tangent line are virtually identical in, maybe up to about here. They're virtually identical. So how can we use this? For example, if I want to know what f of x is here, how could I find out what the point on the tangent line is going to be at, or approximately that space there? Okay. So how do we use the line? Well, if you think about this way, a straight line, in order to get to the next point on the line, there's going to be a rise and there's going to be a run involved, right? A rise and a run. A rise and a run. So what is rise over run? It's the slope of a line, right? Now, the slope of a tangent line is what? Okay, so that's our first main point. You want to write this down. Slope of the tangent line is f prime of x. Okay? The actual slope of this line at a is actually f prime of a. So at x equals a, it's f prime of a. Okay. And so we can also interpret slope as being rise over run. Okay, and this is very important. So if I want to find out, let's just cut some of this now. If I want to find out what a point, let's say over here is, and I knew what the slope of the tangent line was at x equals a, so I have an actual value, I can interpret that as a rise over run. Now, if I have that slope, and I am actually trying to calculate what this value is right here, okay, I can think about this value as f of a plus the rise portion of the slope. Now, the amount of rise also depends on the amount of run. So let's think about this. Rise over run times run, or that is the difference in the x values. What does that give us if we were to multiply that together?
Rise.
That gives us the rise. Okay. So we're getting somewhere now. Okay. If you wanted to find the point on a line and you wanted to use the slope of the point, you would use the slope of that line and you would multiply it by the difference in the x values between the 2 points. Okay?
Slope multiplied by the difference.
Slope multiplied by the difference in the x values, right? So let's say this was the x value here. So this difference, that's change in x, that's my run, change in x. And then I will get the change in y. And if I found this change in y, I could add that to my original f of a, and I would get an approximation here. So I would get an approximation. So let's back up a little bit. I'm going to erase some of this stuff here, clean this up just a little bit for you. Okay, even this. Okay, we've determined this already. So the linear approximation, I don't know what. Let's say I'm going to go to 4.26. Okay, so this looks like 4.26. It's going to be right about here. Now, the difference between the red line and the blue line, virtually nothing, right? So I don't know what the square root of 4.26 is, but I wonder if I could use the slope of the tangent line to find out what the y value of this point is. And so if you think about it, this is what I'm looking at. I'm looking at f of a, and I'm going to add the rise from the slope. So I'm going to add the rise over run times the run to get, and I'm going to call this approximation the L of x. Okay, so this is going to be L of x right here. I don't know if you can, I think you could see that, but this is going to be L of x. That's our linear approximation. And so we're building here now what the linear approximation is of the line of the red function at a certain value is going to be found by doing this. So let's clean this up, because this doesn't look much like calculus. What is the rise over run of this blue line? Well, you already said that. That is it's the tangent. Now, it's the slope of the tangent evaluated at this a value. That's what this is right here. And the difference in the two x values is going to be whatever that x value is minus the a value where we're starting from. Okay? So this is the heart of linear approximations. Again, because the red line on the original graph and the blue tangent line are virtually the same locally around that point, that's called local linearization, that the graph approximates, the tangent line approximates the graph immediately around the point of tangency. We're going to use that fact to estimate. In this case, we're going to estimate what the y value would be at x equals 4.26. So this is what this is the formula for a linear approximation. And again, clean that up a little bit. This is it right down here. The linear approximation using the slope of the tangent is to start off at f of a, whatever a is on your line. That's where the point of tangency is. And you're going to add the derivative evaluated at a times the change in x, or x minus a. So here's the question that we're going to be able to answer now. Okay, and let's just go down here. I've left a little bit too much space for us, but anyways. So here's the question. Without a calculator, use linear approximations to determine the square root of 4.26. So that's what we're going to do. And I've already shown you on the graph sort of what that would look like on the graph. So this is how you approximate. We're going to do this. The linear approximation, this is going to be the linear approximation at 4.26, I guess. Okay? So this is the value right here, 4.26. And I want to know what that value is. I don't have a calculator. I'm going to use linear approximations. So what I'm going to do is I'm going to use f of a, which is what? What's f of a? If I put square root of, if I put 4 into this function, what is that? F of a equals? Yeah, 2. I covered it up here, but this is 1 and 2. See that? So 2, that's f of a. That's just the value that we know, the point of tangency. Okay? Yes? Yeah, I did pick 4 randomly. So I've got 4 because that's a known value. I know what f of a is, no problem. I don't know what f of 4.26 is, but I know what f of a is. Okay, so once again, we don't know what this y value is. See that? I'm trying to find that. I'm trying to find, like, L of x really is this right here. I'm trying to estimate this, approximate this. I don't know what the square root of 4.26 without a calculator. Okay? I do know what this point is, and that is the point 4, 2.
Is it because it is closer to the point that you want to find?
Yes, yes. This is a very close point that is known, and it's So with this, what you want to do is you have to have f of a that you know what the value of y is, because you need that. Okay, so if I know what this value is, I can calculate in the immediate area. I can calculate any point around here using the tangent line. Okay, so yes, I have selected 4.26. because that's a number that's close to a point that I already know, and I will be able to use the local linearization here to approximate it.
Oh, okay.
Okay. If I picked 9, look at if I picked 9, 3 way over here, okay, this wouldn't be a good approximation, would it? The tangent line is not going to work. It's not going to work for anything over here, right? Too much of a difference or whatever. So I'm going to try and find this. Okay. Back to the question here. So 2, everyone see how f of, this is really, a is 4. See, I'm going to put 4 here. Can I do that? 4? You see? Everyone see this? 4 is my point. That's a. That's a in this question. So f of 4 is 2. Now, the derivative evaluated at 4, now that we have to think about. what is, here's my function, what is the derivative? What is it?
1 divided by 2 root x.
1 over 2x?
No, 2 root x.
1 over 2x on the bottom. That's right, because remember, this is a positive 1/2. Take the power rule there, subtract 1. This is negative 1/2. So it's 1 over 2x. Everyone see that? Yes, thank you. 2 root x. Okay? Because this is a square root. Yeah. I thought you said 1 over 2x. Did you say 1 over 2x? You said 1 over 2 root x? Okay, good. So 1 over 2 root x. Now, if x is 4, what is this? 1 over 2 times the square root of 4. 1 over 4. Okay. So this is 1 over 4. And now x is this value that I'm trying to approximate. So this is going to be 4.26 minus 4. So it's the change in x there, right? So the approximation L of x, or L of 4.26, is 2 plus 1/4 times 0.26. So on the calculator, now you don't have to distribute. You can just subtract this, right? It's just 0.26. You don't have to distribute anything. You don't have to use your calculator. No, and we aren't using our well, that's fine. We can not use our calculator, but I'm just saying don't plug the square root of 4.26. That's what I'm saying. I'm not interested in you just plugging square root of 4.26 in and here's my answer. No. You're going to check with the calculator, and if you want to do this, we have to do this with the calculator. So we don't have to, but 0.26 times 0.25 is 0.065 plus 2. And that's what we're going to get for this right here, correct? 2.065. So the approximation of, in this case, the square root of 4.26, we have calculated using linear approximations as a value of 2.065. So if I can clean this up a little bit, this point right here, this point has an x value of 4.26 and a y value of 2.065. You see that? That's the coordinates of this point right here. So let's see how we did. Check with our calculator. Now we can just double check. The square root of 4.26 is, look at that, 2.06397. So we are, just a couple thousandths off, right? Like, I mean, we're pretty close, right? Just a factor of 1,000 there. So pretty close. So that's a very good linear approximation. Now, the difference between these two numbers, right, minus 2.065, this difference right here would be what? What does this difference represent on my graph here? Margin of error. Okay, a little more specific. Thank you. Yes, I heard that. So 4.26. That actually, this number is actually the difference, this difference between the point 4.26 on our tangent line and the point on the actual graph. So it's the difference in y values between those 2 points. So this is how close we were. See? 1,000th, basically. Got it? Okay? Okay, so I'm going to give you guys a chance here. Why don't you guys do an example here, and I want you to find for me the square root of 3.91 using linear approximations.
Do we use the same graph from before?
Sure, you can use the same graph and everything. Why don't you give that one a try? All right, so you should have it set up something like this. F of 4, we said, the square root of 4 is 2. This we've already calculated is going to be 1 over 4, right? And the difference between 3.91 and 4 is going to be a what? A negative what?
0.0225.
Whoa. 0.0, isn't it 0.09?
0.09.
Times 0.25, okay. So what is this going to be? Go ahead. You're a step ahead of me. What's this whole thing right here?
Frozen.
Yeah, it's frozen. That's why I couldn't.
Yeah,
It's frozen. Okay, I'm sorry. All right. So you got 2 times a quarter times, okay. So what have you got here?
Negative 0.0225.
Negative 0.0225.
Yep.
Okay. So what's this then? Equals 2 minus, okay, it's going to be less than 2. It's going to be what?
1.9775.
All right. So it looks like here's our known point. Here is 3.91 approximately. So we can use local linearization there to estimate this. And is this the number that we come up with here? So let's check to see if this is pretty close. And it is, hey? Okay. So the square root of 3.91 is 1.97737. Okay. So we are very, very close. That's a good approximation. Okay? Very good. Now, the last thing I want to talk to you about in this lesson is, okay, that's the one we just did. Okay, here we go. This is the last little bit I want to talk to you about. So find the linearization. Okay, so if you hear that word linearization, it's basically meaning what's the equation that you use? What's the equation that you use? So it's kind of like the equation of a tangent line, right? Like if you want to find the equation of a tangent line, the linearization would be what is L of x, basically. Okay? For this particular context. So what's the linearization? Well, L of x we know is f of a plus f prime of a times x minus a. Okay? And so a is going to be, looks like this number right here. So that's the a value that we're talking about. And we don't have an x value. We don't have an x value here, so we're just going to leave x in the formula. And that's what the linearization is going to be. Okay? So the linearization or the linear approximation is going to be, now what is f of a? That is actually cos of pi over 2, isn't it? Now, we're going to figure out what the antiderivative, what the derivative of evaluated a is in a second. But let's fill out this one first. So this is going to be x minus pi over 2. Okay. So, what is the antiderivative? Why do I keep saying antiderivatives today? Sorry. What is the derivative of cos?
Negative sign.
Negative sine. Very good. Now, evaluated at a would be negative sine of pi over 2. Does that make sense? So this is going to be negative sine pi over 2. Okay. So we should simplify this. Maybe a little, if we can. So what's cos of pi over 2?
0.
Okay, so
1
0,
is
1. What is it?
0.
It's got to be 1.
0, 1. Which one is it?
0. 0.
Okay, so pi over 2 is 0. That's okay. Minus, what's sine of pi over 2?
1.
1, thank you. Times x minus pi over 2. So let's distribute a little bit of that here. So we have negative x plus pi over 2. And that is the linearization. So that's how you could use the tangent line to approximate a value that's very close to pi over 2. Okay? Now, the second part of the question, this is really B, it says use this to calculate cos of 1.75. So now 1.75 is,
X.
yeah, it's our x. So let's see if that actually works. L of 1.75 here is going to be negative 1.75 plus pi over 2. So negative 1.75 plus pi over 2. Negative 1.75 plus pi divided by 2 is going to be negative 0.1792. Okay, let's see if that's close. So cos of 1.75, and of course that would have to be radians, right? Okay. Cos 1.75. Okay, let's hope and pray. Oh, look at that. Pretty darn close. See that? So there you go. Sorry? Well, is it close enough? Okay, that's a good question. Is it close enough? Now, the further away you go from your A value, the more disparity you're going to have, right? Is it close enough? This is the best approximation that we have. Yeah. So if you can use a point, the A value, girls, if you can find a point that's closer to the one you're looking for, that you can use for your linearization, then your approximation will be better. Okay, so say that again. If you can find a point like this is x equals pi over 2, right? So 1.75 is pretty close to pi over 2. If you had an A value that's closer to 1.75, let's say, then your approximation is going to be better. So that's kind of a relative question there. But if you come up with a question like this is exactly how you would do it. You would use what you're given, write the linearization, and then use that to estimate. Now, if we estimated something like 2.75, right, we're going to be way off. Okay? Because think about cos. Shh, girls. Right, think about cos. So where's pi over 2 here? There's 2 pi. There's pi. Here's pi over 2. Right? So 1.75, okay? Right? That's right around here. But 2.75, right? That would be closer to over here. So if we used the linearization here at pi over 2, if we use this tangent line to estimate this value, you see how it's not going to work at all? So it's only locally. So we would get a value of like down here, which is very different. So yeah, so the further away you go from this point of tangency, the worse your approximation is going to be. Okay, so that's our lesson for today for linear approximations, and also linearization, and hopefully you understand sort of the concept behind that.